Greetings, dear friends! Today we are embarking on an incredible journey through the vastness of our solar system. This is our cosmic home, a unique, dynamic, and fascinating system that formed billions of years ago and still holds countless mysteries. We'll explore the structure of the solar system, its place in the universe, and why studying it is so important. So get ready for an exciting journey through science and history. The solar system is a vast gravitational system, with our star, the Sun, at its center. It includes 8 planets orbiting the Sun, more than 200 known moons, countless asteroids, comets, and clouds of interplanetary dust. All of these objects are bound together by gravity, forming a complex yet harmonious structure. The scale of the solar system is hard to imagine. Including the Oort cloud, its diameter stretches to about 2 light years, roughly 19 trillion kilometers. Imagine this. If the Sun were the size of a soccer ball, the Earth would be just 30 meters away and only the size of a pinhead. About 4.5 billion years ago, a massive cloud of gas and dust began to collapse under gravity. At its center, a dense core formed, the precursor of the Sun, which soon began to shine through nuclear fusion. The remaining material formed a spinning disk, from which planets, moons, and other celestial bodies gradually emerged. Understanding this process is key to learning how star systems form throughout our galaxy. The solar system is a unique laboratory for studying the processes that occur in other star systems. Our solar system is located in the Milky Way galaxy, which contains between 100 and 400 billion stars. We reside in the Orion spiral arm, roughly 27,000 light years from the galactic center. This is a relatively calm region, which likely played an important role in creating conditions suitable for life. Let's take a closer look at spiral arms. They are the main structures of spiral galaxies, appearing as bright, winding regions filled with star-forming clouds, gas, and dust. Our arm lies between 2 larger structures, the Perseus arm and the Centaurus arm. This position provides relative safety, keeping us far from the galactic center, where activity is much higher. The solar system moves around the center of the galaxy at a speed of about 828,000 kilometers per hour. However, a full orbit takes between 225 and 250 million years. This period is known as a galactic year. The last time we were in this part of the galaxy, dinosaurs roamed the Earth. Incredibly, if you could view the Milky Way from the outside, the solar system would appear as barely a speck among billions of stars. Yet, it is on this tiny speck that life arose, a phenomenon we have not yet discovered anywhere else in the universe. Let's begin with how our understanding of our place in the cosmos has changed. In ancient times, people believed that the Earth was the center of the universe. This idea was based on the geocentric model proposed by Ptolemy, which remained the dominant view in astronomy for about 1,500 years. According to the geocentric model, all celestial bodies, including the Sun, the Moon, and the stars, revolve around the Earth. However, the 16th century brought a major turning point in the history of astronomy. Nicolaus Copernicus, a Polish astronomer, proposed that the Earth is not the center of the universe, but just one of the planets orbiting the Sun. This discovery laid the foundation for the new heliocentric model. Unsurprisingly, this idea faced strong resistance, as it challenged centuries-old beliefs about humanity's place in the cosmos. Yet Copernicus set the stage for a revolution in astronomy. The next key breakthrough came thanks to Galileo Galilei. In the early 17th century, using an improved telescope, Galileo became the first person to observe the moon's surface, discovering its craters and mountains, which contradicted the idea of a perfect celestial sphere. He also observed the phases of Venus, providing strong evidence in favor of the heliocentric model. These observations confirmed Copernicus' hypothesis and forced a rethinking of the foundations of astronomy. At the end of the 17th century, Isaac Newton completed this transformation. Through his laws of gravity, he explained why planets move in orbits around the sun. Newton showed that gravity is the force that keeps all celestial bodies, from the moon to the farthest planets, in their orbits. His work became the cornerstone of classical mechanics and allowed for much more precise predictions of planetary motion. From the late 19th century, and especially in the 20th century, humanity entered the era of practical space exploration. In 1969, the Apollo program successfully sent humans to the moon. With the development of spacecraft and telescopes, we began actively exploring not only nearby planets, but also the farthest reaches of the universe. The Hubble Space Telescope, launched in 1990, opened entirely new horizons, providing astronomers with incredibly precise data on stars, galaxies, and other celestial objects. Thus, the journey from the geocentric model to our modern understanding of the cosmos has been shaped by crucial discoveries and revolutionary ideas that fundamentally changed the way we see the universe. After exploring the key stages in the development of astronomy and our understanding of the cosmos, let's turn our attention to the planets closest to the Sun, known as the inner planets. These are Mercury, Venus, Earth, and Mars. They form a unique group of bodies with rocky surfaces, standing in stark contrast to the giant planets in the outer regions of the solar system. Let's begin with the smallest, yet very intriguing planet, Mercury. Mercury is the closest planet to the Sun, and everything about it is shaped by this proximity. It lies about 0.39 astronomical units from the Sun, or a little less than half the distance between the Earth and the Sun, since 1 astronomical unit equals about 150 million kilometers. Mercury is, on average, only 58 million kilometers away from our star. This makes it the very first planet in the lineup of our solar system. Mercury is a dwarf among planets. With a diameter of about 4,800 kilometers, roughly 2.5 times smaller than Earth's, despite its tiny size, it is denser than many other planets thanks to its enormous iron core. Mercury completes a full orbit around the Sun in just 88 Earth days, giving it the shortest year of any planet. Its rotation, however, takes 59 Earth days. Because of a complex interplay between rotation and orbit, one solar day on Mercury, from sunrise to sunrise, actually lasts 176 Earth days. This unusual phenomenon is the result of an orbital rotational resonance. For every 3 orbits around the Sun, Mercury rotates on its axis twice. The resonance is caused by the Sun's tidal forces, which gradually slowed the planet's spin out. Mercury has no thick atmosphere to trap heat, leading to extreme temperature swings between day and night. On the daytime side, temperatures soar to 430 degrees Celsius, hot enough to melt lead, while the nighttime side plunges to minus 180 degrees Celsius. This contrast is among the most extreme in the solar system. Structurally, Mercury is mostly metal. Its core makes up about 75% of the planet's diameter, disproportionately large compared to other worlds. Composed mainly of iron and likely partly liquid, the core generates a weak magnetic field, about 100 times weaker than Earth's, even. So this field creates a magnetosphere that interacts with the solar wind. The planet's outer shell, or crust, is very thin, only about 20 kilometers thick. Mercury's surface is heavily cratered, scarred by intense asteroid and meteorite impacts during the early years of the solar system. One of the most striking features is the Caloris Basin, a massive crater more than 1,300 kilometers across. The impact that formed it was so powerful that it deformed the terrain on the opposite side of the planet. The exploration of Mercury began with NASA's Mariner 10 mission in the 1970s, which returned the first detailed images of the surface and revealed the existence of a magnetic field. A true leap forward came with the Messenger mission in the 2000s, which orbited the planet, mapped its surface composition, measured its magnetic field, and uncovered a wealth of geological details. Mercury is, in many ways, a window into the early history of the solar system. Its surface has remained largely unchanged for billions of years, preserving the record of planetary formation processes. Its unusual structure and orbital behavior provide scientists with vital clues about gravitational interactions, the influence of stars on nearby planets, and the cooling of planetary cores. Next comes a mysterious world, Venus, a planet so extreme that it has earned the title of the hellish planet. Venus is the second planet from the Sun and Earth's closest neighbor, remarkably similar to our planet in both size and mass. It is often called Earth's sister, but the resemblance ends with the numbers. Venus is a true cosmic inferno. Scorching heat, clouds of acid, and atmospheric pressure strong enough to crush most spacecraft within minutes. Yet behind these extreme conditions lies a story that may reveal what could have happened to Earth if its delicate balance had been disrupted in terms of size. Venus really does mirror Earth. Its diameter is about 12,000 kilometers, only about 5% smaller than our own planet. Venus has a mass equal to about 82% of Earth's, and both its density and surface gravity are strikingly similar to ours. If you were standing on its surface, you would weigh almost the same as you do on Earth. Venus orbits the Sun at a distance of about 0.72 astronomical units, or roughly 108 million kilometers. That is closer than Earth, but not nearly enough to explain its incredibly high surface temperatures. The true cause of Venus's catastrophic conditions lies in its unique atmosphere. The atmosphere of Venus is one of the most extreme in the solar system. It is composed of 96% carbon dioxide, with small amounts of nitrogen and traces of sulfur compounds. The upper layers are shrouded in thick clouds of sulfuric acid, which block sunlight from reaching the surface. This is why Venus appears so bright and shiny in our night sky. Its clouds reflect about 70% of incoming solar radiation. Beneath those clouds, however, lies a true nightmare. The atmospheric pressure on Venus is 92 times greater than on Earth, equivalent to the pressure you would experience 1 kilometer beneath the ocean's surface. Any base you might try to build there would be crushed in moments. Venus also has the hottest surface of any planet in the solar system, reaching 470 degrees Celsius. That's even hotter than Mercury, despite being farther from the Sun. The main reason is a runaway greenhouse effect that completely reshaped the planet's atmosphere and climate in the distant past. Venus may have had conditions more similar to Earth's. There is even a possibility that liquid water once existed on its surface. But its closeness to the Sun played a decisive role in a catastrophic transformation. Intense solar radiation caused temperatures to rise, water to evaporate, and steam, a powerful greenhouse gas, to amplify the heating effect. At the same time, volcanic activity released vast amounts of carbon dioxide, which accumulated in the atmosphere, thickening and intensifying the greenhouse effect. Today, the dynamics of Venus's atmosphere are unlike anything else. Nearly 100% of the heat that reaches the planet is trapped within its dense carbon dioxide blanket, creating the most extreme example of the greenhouse effect in the solar system. The upper layers of Venus's clouds reflect about 70% of sunlight, but the remaining 30% that reaches the surface is absorbed and then trapped beneath the dense layer of carbon dioxide, unable to escape back into space. This process turns Venus into a true heat trap. Temperatures on Venus remain remarkably stable across the entire planet, with almost no variation between day and night or between the equator and the poles. The thick atmosphere distributes heat so evenly that even during the night, when the sun no longer shines on the surface, the temperature stays nearly the same as in the daytime. Beneath this heavy atmosphere lies a hidden world. Because the thick cloud cover blocks ordinary optical observations, the surface of Venus has been explored mainly with radar, which can penetrate the clouds and reveal features invisible to conventional telescopes. Venus is truly a planet of volcanoes. Its surface is almost entirely covered by vast lava plains formed during ancient eruptions. One of the planet's tallest features is Maxwell Montes, a mountain range that rises about 11 kilometers high, even taller than Mount Everest on Earth. Yet most of Venus's surface is relatively flat, dotted with strange geological formations, such as coronae, enormous circular structures created by intense volcanic activity. These features are remnants of powerful tectonic processes that took place billions of years ago. Interestingly, despite its volcanic landscape, Venus shows no clear signs of plate tectonics like those on Earth. Instead, its crust bends and cracks under the pressure of rising magma, giving rise to unique surface shapes and patterns dotted about 60 kilometers above the surface. Incredibly strong winds blow at speeds of up to 360 kilometers per hour. This phenomenon is known as superrotation. The atmosphere circles the planet far faster than the surface itself. Venus rotates on its axis once every 243 Earth days, the slowest rotation of any planet. Meanwhile, its year lasts just 225 Earth days. In other words, a day on Venus is longer than its year. Venus was also one of the first planets to be studied by spacecraft. The Soviet Venera missions were the pioneers, sending probes that actually landed on the surface. Venera 7, for example, transmitted the first direct data from Venus, though it survived for barely 30 minutes under the planet's crushing heat and pressure. Later, the European Space Agency's Venus Express explored the atmosphere, studying its powerful winds and the chemistry of its clouds. Today, exciting new missions are on the horizon. NASA's planned Da Vinci Plus and Veritas missions aim to map Venus's surface in detail and probe its inner structure. These studies may help answer one of the most intriguing questions in planetary science: could Venus have once been habitable in its distant past? Earth is our home, the only planet in the solar system known to harbor life. It is the third planet from the Sun, orbiting at a distance of 1 astronomical unit, or about 150 million kilometers. This just right distance places Earth in what scientists call the habitable zone, where liquid water can exist on the surface, a key ingredient for life as we know it in terms of size. Earth has a diameter of about 12,700 kilometers, making it the largest of the rocky inner planets. Its mass and gravity provide the perfect balance to hold on to a life-sustaining atmosphere, without crushing everything beneath it. This atmosphere is a delicate mix of nitrogen, oxygen, and trace gases. It not only allows us to breathe, but also protects us by filtering harmful solar radiation and moderating the planet's temperature. Earth is a world shaped by dynamic processes. Plate tectonics constantly reshapes its surface, driving the formation of mountains, earthquakes, and volcanic eruptions. Unlike Venus, whose crust bends under pressure, Earth's crust is divided into massive plates that slowly drift across the globe. This movement recycles materials, regulates the climate through the carbon cycle, and has played a key role in making Earth stable enough for life over billions of years. Earth also has a powerful magnetic field, generated by the motion of molten iron in its outer core. This invisible shield deflects much of the solar wind, protecting both our atmosphere and life from harmful charged particles streaming from the sun. Perhaps Earth's most remarkable feature is the abundance of liquid water. Covering more than 70% of the planet's surface, oceans not only shape the climate but also cradle an astonishing diversity of life. From the smallest microorganisms to the largest whales, water has been the stage upon which life first appeared and evolved. Oceans act as Earth's great climate engine, absorbing heat from the sun and redistributing it through powerful currents, softening extremes between day and night, summer and winter. The water cycle evaporation, condensation, and rainfall connects land, sea, and atmosphere in a continuous rhythm that sustains ecosystems across the globe. What makes Earth truly unique among its planetary neighbors is this delicate balance. On Venus, heat long ago boiled away any surface water. On Mars, most of it lies frozen beneath dust and rock. And Mercury, scorched by the sun, holds only traces of ice and permanent shadows. Earth alone keeps vast oceans of liquid water under, an atmosphere that shields and nurtures life. For humanity, water has always been more than a scientific curiosity. It is the foundation of civilization. The first great cities rose along rivers, seas became highways for trade and exploration. And even today, oceans connect our continents and economies. In this way, water is not just the essence of Earth's natural beauty, but also the quiet architect of human history. Orbitally, Earth takes 365 days to circle the sun, giving us our year, while its 24-hour rotation creates the cycle of day and night. The tilt of its axis adds another layer of richness, producing the seasons that govern much of life's rhythm across the globe. For humanity, Earth is more than a planet. It is a cradle of civilization, science, and exploration. From this small blue world, we have looked outward, studied our neighbors, and begun to imagine journeys beyond. Yet, no matter how far we travel, Earth remains our only known oasis in the vastness of space. The moon is Earth's only natural satellite and one of the most fascinating objects in our sky. It orbits the Earth at an average distance of about 384,000 kilometers and has a diameter of roughly 3,474 kilometers, about a quarter of Earth's size. Despite its relatively small size, the moon has a profound influence on our planet. Its gravity generates the ocean tides, shaping coastal ecosystems and affecting currents that help regulate Earth's climate. The moon also stabilizes the tilt of Earth's axis, keeping the seasons consistent over long periods and contributing to a stable environment for life. The surface of the moon is a striking landscape of contrasts. Vast plains called Maria were formed by ancient volcanic activity and appear as the dark regions visible from Earth. These are punctuated by countless craters, created by billions of years of impacts from asteroids and comets. Some craters, like Tycho and Copernicus, have bright rays extending outward, evidence of relatively recent impacts in geological terms. Mountain ranges and riles, long, narrow channels, add further complexity to the lunar terrain. The moon has no significant atmosphere, which means temperatures swing dramatically from blistering heat and sunlight up to 127 degrees Celsius to freezing cold and shadow, down to minus 173 degrees Celsius without an atmosphere. There is no weather to reshape the surface, so the moon preserves a record of the solar system's history stretching back billions of years. Humans have long been captivated by the moon. Its phases have guided calendars and inspired myths and art. Throughout history, the space age transformed our understanding. The Apollo missions of the 1960s and 70s not only put humans on the lunar surface, but also brought back rocks and soil that revealed the moon's origin, composition, and geological history. These samples confirmed that the moon likely formed from debris after a giant impact between the early Earth and a Mars-sized body. giving us key insights into the formation of our planet and the solar system as a whole. Today, the moon continues to be a focus of exploration. Robotic missions study its surface, search for water ice and permanently shadowed craters, and prepare for future human settlement. The moon is not just a satellite, it is a window into the past, a stabilizing partner for Earth, and a stepping stone for humanity's journey deeper into space. Mars, often called the Red Planet, is the fourth planet from the Sun and Earth's outer neighbor. Its reddish hue, visible even to the naked eye, comes from iron-rich dust covering its surface. Mars is about half the size of Earth, with a diameter of roughly 6,780 kilometers, yet it has captured human imagination. Like no other planet besides our own, the surface of Mars is a world of extremes and contrasts. Vast plains, towering volcanoes, deep canyons, and polar ice caps create a landscape both beautiful and harsh. Olympus Mons, the tallest volcano in the solar system, rises nearly 22 kilometers high, almost 3 times the height of Mount Everest. Valles Marineris, a system of canyons stretching over 4,000 kilometers, is so vast that it would span the entire continental United States if placed on Earth. Other regions, like the northern plains, are flat and dusty, while the southern highlands are heavily cratered, and ancient Mars has a thin atmosphere, composed mostly of carbon dioxide with traces of nitrogen and argon. This thin air cannot trap heat effectively, so temperatures fluctuate widely, from about 20 degrees Celsius at the equator during the day to minus 125 degrees Celsius at night near the poles. The low atmospheric pressure also means liquid water cannot persist on the surface for long. Yet evidence of dried riverbeds, sedimentary deposits, and ancient lake beds suggests that billions of years ago, Mars may have had a warmer, wetter climate capable of supporting microbial life. Today, water exists mainly as ice at the poles or beneath the surface, and small amounts of vapor appear in the atmosphere. Seasonal flows of briny water, called recurring slope linea, hint at the possibility that liquid water may still occasionally appear. The planet's surface is scarred with craters, evidence of billions of years of cosmic impacts, and shaped by winds that drive massive dust storms capable of enveloping the entire planet. Some of these storms last for months, reducing visibility and affecting surface temperatures. Mars experiences seasons similar to Earth's due to its tilted axis, though they last almost twice as long because a Martian year is 687. Earth days. Mars has been the focus of extensive exploration. Early flybys and orbiters mapped the planet's surface and polar caps, while landers and rovers such as Viking, Spirit, Opportunity, Curiosity, and Perseverance have explored the ground in detail. These missions have analyzed rocks, soil, and the atmosphere, uncovering evidence of ancient water flows, complex geology, and organic molecules, the building blocks of life. The InSight lander has studied Mars' interior, revealing details about its core, crust, and seismic activity, giving us insights into how rocky planets evolve. The planet's 2 small moons, Phobos and Deimos, are likely captured asteroids. They orbit Mars closely and irregularly, presenting potential targets for future exploration. Phobos, the larger of the 2, is slowly spiraling inward and may eventually break apart, forming a ring around Mars millions of years from now. Mars continues to inspire scientific discovery and human imagination. Current and planned missions such as NASA's Mars Sample Return, ESA's ExoMars, and various private initiatives aim to return samples, search for signs of past or present life, and study the feasibility of human colonization. With its dramatic landscapes, hints of ancient water, and intriguing moons, Mars serves as both a laboratory for understanding planetary evolution and a stepping stone for humanity's future beyond Earth. Jupiter, the giant of our solar system, is the fifth planet from the Sun and by far the largest. With a diameter of about 140,000 kilometers, more than 11 times that of Earth, it is a true colossus, holding more than twice the mass of all the other planets combined. Its immense gravity shapes the orbits of countless moons, asteroids, and comets, making Jupiter a central figure in the architecture of the solar system. Unlike the rocky inner planets, Jupiter is a gas giant, composed mostly of hydrogen and helium. It has no solid surface as we know it. Instead, the atmosphere gradually transitions into a dense, hot interior. The planet is famous for its colorful cloud bands, created by high-speed winds that reach up to 620 kilometers per hour. The most iconic feature, the Great Red Spot, is a massive storm larger than Earth that has raged for at least 400 years. These clouds are also home to countless smaller storms, lightning flashes, and turbulent vortexes, creating a dynamic, ever-changing system. Jupiter rotates astonishingly fast. A single rotation takes just under 10 hours, making its day the shortest. Among all planets, this rapid spin causes the planet to bulge at the equator, giving it a slightly flattened appearance. Beneath its swirling clouds lies a complex interior. A layer of molecular hydrogen transitions into metallic hydrogen under immense pressure, generating a powerful magnetic field. Deep down, Jupiter may harbor a dense core of rock and ice, though its exact composition is still a subject of study. The planet's magnetic field is the strongest in the solar system, 20,000 times stronger than Earth's, and it traps charged particles, creating intense radiation belts around the planet. Jupiter is orbited by a vast system of more than 90 confirmed moons, ranging from tiny, irregularly shaped bodies to massive worlds like Ganymede, the largest moon in the solar system, which is even bigger than Mercury. Europa, another moon, is particularly intriguing. Beneath its icy crest lies a global subsurface ocean that could potentially support life. Io, the most volcanically active body in the solar system, constantly reshapes its surface with molten lava, while Callisto's ancient, cratered surface preserves a record of billions of years of impacts. These moons offer scientists a natural laboratory to study geology, potential habitability, and tidal interactions. Exploration of Jupiter began with flybys from the Pioneer and Voyager spacecraft in the 1970s, providing the first detailed images and measurements. The Galileo mission in the 1990s sent an orbiter and probe that entered Jupiter's atmosphere, giving unprecedented insights into its composition, cloud structure, and moons. Today, NASA's Juno spacecraft continues to orbit Jupiter, mapping its gravitational and magnetic fields, analyzing the planet's deep atmosphere, and helping scientists understand its formation and evolution. Jupiter is not only a spectacular world in itself, but also a guardian and influencer of the solar system. Its gravity has shaped the orbits of other planets, guided the movement of comets and asteroids, and even protected the inner planets, including Earth, from frequent catastrophic impacts. As a gas giant, it represents a class of planets that are common in other star systems, making Jupiter a crucial reference point in understanding planets beyond our own solar system. Saturn, the sixth planet from the Sun, is famous for its breathtaking system of rings and its status as the second largest planet in the solar system. With a diameter of about 120,000 kilometers, nearly 10 times that of Earth, Saturn is a gas giant composed primarily of hydrogen and helium. Its low density is so remarkable that if there were a body of water large enough, Saturn would float. The planet's most striking feature is its extensive ring system, made up of countless particles of ice and rock ranging from tiny grains to massive boulders. These rings form intricate patterns, with gaps and divisions caused by the gravitational influence of Saturn's moons, known as shepherd moons. The rings are not solid. They are a delicate, dynamic structure, constantly shifting under the influence of Saturn's gravity and the orbital motions of its moons. Saturn's atmosphere is a layered system of clouds composed of ammonia, methane, and water vapor. Winds on Saturn are extremely fast, reaching up to 1,800 kilometers per hour near the equator, making it one of the windiest planets in the solar system. The planet exhibits spectacular storms and long-lived vortices, including the famous hexagonal jet stream at its north pole, a unique geometric formation that has fascinated scientists for decades. Like Jupiter, Saturn has no solid surface. Its interior gradually transitions from a gaseous envelope to layers of metallic hydrogen and, deep within, possibly a dense core made of rock and ice. The rapid rotation of Saturn, taking about 10.7 hours per day, causes the planet to bulge. At the equator, giving it a noticeably flattened shape, Saturn also generates a powerful magnetic field, though weaker than Jupiter's, which interacts with its many moons and contributes to spectacular auroras near the poles. Saturn's system of moons is extensive, with over 80 confirmed satellites. Among them, Titan and Enceladus stand out for their unique features and scientific importance. Titan, Saturn's largest moon, is larger than Mercury and possesses a thick, nitrogen-rich atmosphere. Its surface hosts lakes, rivers, and dunes, made of liquid methane and ethane, creating landscapes strikingly similar to Earth's hydrological features, though with entirely different chemistry. Titan offers a natural laboratory for studying prebiotic chemistry and the processes that might lead to life in environments very different from our own. Enceladus, though smaller, is no less fascinating. Its icy surface is covered with cracks and geysers that erupt water vapor and ice into space, forming a tenuous atmosphere and contributing to one of Saturn's rings. Beneath this icy crust lies a global subsurface ocean, heated by tidal forces from Saturn's gravity. The possibility of liquid water and the presence of organic compounds make Enceladus one of the most promising locations in the solar system. To search for life beyond Earth, exploration of Saturn has been revolutionized by missions such as Pioneer, Voyager, and the groundbreaking Cassini-Huygens mission. Cassini orbited Saturn for over 13 years, providing detailed observations of the planet, its rings, and its moons. The Huygens probe even landed on Titan, sending back unprecedented images and data about its rivers, dunes, and atmospheric chemistry. Saturn is more than just a ringed beauty. It is a complex, dynamic world that continues to challenge our understanding of planetary systems. Its rings, storms, and moons offer scientists a window into processes that shape the early solar system, and its moons, especially Titan and Enceladus, are prime targets in the ongoing search for extraterrestrial life. Saturn remains a jewel of the solar system, both in beauty and scientific importance. Uranus, the seventh planet from the Sun, is a mysterious and unique world in our solar system. With a diameter of about 51,000 kilometers, it is nearly 4 times wider than Earth, making it the third largest planet by size. Unlike Jupiter and Saturn, Uranus is classified as an ice giant, composed mainly of water, ammonia, and methane ices, with a relatively small rocky core surrounded by a thick atmosphere of hydrogen and helium. Its striking blue-green color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green wavelengths. One of the most extraordinary features of Uranus is its extreme axial tilt of about 98 degrees. Essentially, the planet rotates on its side, with its poles pointing almost directly at the Sun. This unusual orientation results in extreme seasonal variations. Each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. This unique rotation profoundly affects the planet's atmosphere and weather patterns, producing winds that can reach speeds up to 900 kilometers per hour. Uranus has a faint system of rings and 27 known moons. Its rings are dark and narrow, composed mostly of small particles of rock and dust. Among its moons, Titania, Oberon, Umbriel, Ariel, and Miranda stand out. Miranda, in particular, is remarkable for its heavily fractured surface, with giant cliffs, canyons, and strange patchwork terrains, suggesting a history of intense geological activity. The atmosphere of Uranus is relatively calm compared to other giant planets, but it occasionally experiences storms and bright cloud features, particularly in the upper layers. Methane ice clouds, combined with a deep blue-green haze, create a mesmerizing appearance that distinguishes Uranus from its planetary neighbors. Beneath its atmosphere, high-pressure ices and a possible superheated water ammonia ocean may exist, offering a glimpse into the complex interiors of ice giants. Exploration of Uranus has been limited. The only spacecraft to visit the planet directly was Voyager 2 in 1986, which provided invaluable images and data on its atmosphere, rings, and moons. Despite the scarcity of missions, Uranus continues to captivate scientists due to its unusual rotation, extreme seasons, and the potential insights it offers into the formation and evolution of ice giants in our solar system and beyond. Uranus is a silent giant, a world of icy mysteries tilted sideways, reminding us that the solar system is filled with surprises, and that even planets seemingly distant and calm hold secrets waiting to be discovered. Neptune, the eighth planet from the Sun, is the outermost giant of our solar system, a distant world of striking blue hues and powerful winds. Slightly smaller than Uranus, with a diameter of about 49,500 kilometers, Neptune is also classified as an ice giant composed mainly of water, ammonia, and methane ices surrounding a dense, rocky core, with a thick atmosphere of hydrogen, helium, and methane. Its brilliant blue color comes from methane in the atmosphere. Absorbing red light and reflecting blue. Neptune is famous for its extreme and dynamic weather. It hosts the fastest winds in the solar system, reaching speeds up to 2,100 kilometers per hour, creating massive storms and vortices in its upper atmosphere. The most famous of these was the Great Dark Spot, a storm comparable in size to Earth observed by Voyager 2 in 1989. Despite its distance from the Sun, Neptune radiates more heat than it receives, suggesting internal processes that drive its energetic atmosphere. The planet is orbited by 14 known moons, with Triton being the largest and most intriguing. Triton is unique among large moons because it orbits Neptune in a retrograde motion, opposite to the planet's rotation, indicating it was likely a captured object from the Kuiper Belt. Triton's surface is icy and geologically active, featuring geysers that erupt nitrogen gas and a thin, frozen crust that records a history of internal activity. Other moons, like Proteus and Nereid, are smaller but add to the complexity of Neptune's satellite system. Neptune also has a system of faint rings, much darker and more fragile than Saturn's, composed of ice and dust particles. These rings are incomplete and appear as arcs rather than continuous bands, shaped by the gravitational influence of nearby moons. Exploration of Neptune has been extremely limited. Voyager 2 remains the only spacecraft to visit the planet directly, providing the first detailed observations of its atmosphere, rings, and moons. Modern telescopes and space missions continue to study Neptune from afar, revealing its storms, dynamic atmosphere, and the intriguing potential of its moons as targets for future exploration. Neptune stands as a reminder that even at the far edges of our solar system, planets are vibrant, active worlds. Its intense winds, icy composition, and enigmatic moons make it a captivating laboratory for understanding the nature of ice giants and the processes that shape distant planetary systems. Pluto, once considered the ninth planet of the solar system, is now classified as a dwarf planet. Located in the distant Kuiper belt beyond Neptune, Pluto is a small, icy world with a diameter of about 2,377 kilometers, roughly 2/3 the size of Earth's moon. Despite its diminutive size, Pluto has captivated scientists and the public alike with its intriguing geology and complex atmosphere. Pluto's surface is a patchwork of diverse terrains. Vast plains of nitrogen ice, such as the famous Sputnik Planitia, coexist with rugged mountains of water ice, some reaching heights of up to 3,500 meters. The surface also features valleys, cliffs, and large craters, showing a history of both impacts and internal geological activity. Remarkably, Pluto exhibits signs of ongoing surface changes, suggesting that it may still be geologically active despite its small size and distance from the Sun. The dwarf planet has a thin atmosphere, primarily composed of nitrogen with traces of methane and carbon monoxide. This atmosphere expands as Pluto approaches the Sun and partially freezes back onto the surface as it moves farther away in its elongated orbit. Temperatures on Pluto are extremely low, averaging around -229 degrees Celsius, making it one of the coldest worlds in the solar system. Pluto is accompanied by 5 known moons, the largest of which is Charon. Charon is so massive relative to Pluto that the two bodies actually orbit a point in space between them, forming a binary system. The other moons, Styx, Nix, Kerberos, and Hydra, are smaller and irregularly shaped, likely captured objects or fragments from ancient collisions. The Pluto-Charon system offers unique insights into tidal interactions, orbital dynamics, and the evolution of small icy bodies in the outer solar system. Our understanding of Pluto was revolutionized by NASA's New Horizons mission, which flew past the dwarf planet in 2015. The spacecraft provided the first close-up images and detailed measurements, revealing Pluto's surprising geological diversity, its icy plains, towering mountains, and complex atmosphere. These discoveries transformed our view of Pluto from a distant, cold dot to a vibrant and dynamic world. Pluto reminds us that even the farthest reaches of the solar system are filled with fascinating worlds. Its icy landscapes, moons, and ongoing activity offer a window into the processes that shape the Kuiper belt, and by extension, the early solar system. Neptune stands as a reminder that even at the far edges of our solar system, planets are vibrant, active worlds. Its intense winds, icy composition, and enigmatic moons make it a captivating laboratory for understanding the nature of ice giants and the processes that shape distant planetary systems. The Sun is at the heart of our solar system, a massive sphere of hot plasma that sustains life on Earth and governs the motions of all planets, moons, and smaller bodies. Containing about 99.8% of the total mass of the solar system, the Sun's immense gravity keeps planets in orbit and shapes the structure of our cosmic neighborhood. It is a G-type main sequence star, often called a yellow dwarf, with a diameter of roughly 1.39 million kilometers, over 100 times larger than Earth, and it could fit more than 1 million Earths inside its volume. The Sun is composed mainly of hydrogen, about 74%, and helium, about 24%, with trace amounts of heavier elements such as oxygen, carbon, and iron. At its core, temperatures reach 15 million C, and nuclear fusion converts hydrogen into helium, releasing enormous energy in the form of light and heat. This energy slowly moves outward through the radiative and convective zones, taking thousands of years to reach the surface. Once it escapes the photosphere, sunlight reaches Earth in about 8 minutes and 20 seconds, powering life and driving Climates. The Sun is a dynamic star. Its surface, the photosphere, is about 5 degrees Celsius and is marked by sunspots, cooler, magnetically active regions. Above it lies the chromosphere, where spicules of gas rise, and the corona, the Sun's outer atmosphere, extending millions of kilometers into space. The corona is visible during solar eclipses and is surprisingly hotter than the photosphere. With temperatures exceeding 1 million C, the Sun produces solar flares and coronal mass ejections, which send bursts of charged particles into space. When these particles interact with Earth's magnetic field, they create auroras but can also disrupt satellites, communication systems, and power grids. Solar activity follows an 11-year cycle, alternating between periods of high and low sunspot activity, affecting space weather across the solar system. Its gravitational pull keeps all planets, asteroids, and comets in stable orbits, shaping the architecture of the solar system. Its light and heat regulate planetary climates, while the solar wind interacts with planetary magnetospheres, shaping phenomena like Jupiter's radiation belts or Saturn's auroras. Without the Sun's energy, Earth would be a frozen, lifeless world. Currently about 4.6 billion years old, the Sun is in the middle of its life cycle. It will continue fusing hydrogen into helium for roughly another 5 billion years. Eventually, it will expand into a red giant, engulfing Mercury, Venus, and possibly Earth, before shedding its outer layers and leaving behind a white dwarf, a dense, slowly cooling stellar remnant. The Sun is more than just a source of light and heat. It is the engine that drives the rhythms of our planet, the day-night cycle, seasons, weather, and the delicate balance that allows life to thrive. Studying the Sun helps us understand not only our solar system, but also the countless other stars that populate our galaxy, offering insights into the formation, evolution, and fate of planetary systems. In essence, the Sun is the glowing heart of our cosmic neighborhood, a dynamic, living star that connects all worlds in the solar system and sustains the delicate web of life on Earth. Asteroids are rocky remnants from the early formation of the solar system, small worlds that never coalesced into planets. They are often irregularly shaped and range in size from tiny pebbles to hundreds of kilometers across. Most asteroids are found in the asteroid belt, a vast region between the orbits of Mars and Jupiter, though some travel closer to Earth or farther into the outer solar system. The asteroid belt contains millions of these objects, from tiny fragments to massive bodies like Ceres, the largest, which is about 940 kilometers in diameter and is classified as a dwarf planet. Asteroids are composed primarily of rock and metal, though some contain carbon-rich compounds or even ice. Studying their composition provides crucial insights into the materials that built the planets and the conditions of the early solar system. Asteroids are not static. Their orbits can be influenced by the gravity of planets, collisions with other asteroids, and even the pressure of sunlight in a phenomenon called the Yarkovsky effect. Some asteroids have moons or are part of binary systems, demonstrating the diversity and complexity of these small bodies. Although they are small compared to planets, asteroids have captured human imagination because of their potential to impact Earth. Scientists actively track near-Earth asteroids to predict possible collisions and to study ways to mitigate them. Missions such as NASA's OSIRIS-REx and Japan's Hayabusa 2 have successfully visited asteroids, collecting samples and returning them to Earth, offering a treasure trove of information about the solar system's building blocks. Asteroids serve as windows into the past, preserving ancient materials largely unchanged for billions of years. They reveal the story of the early solar system and help us understand the processes that shape the planets, including our own Earth, beyond science. They are also considered as potential sources of valuable minerals for future space exploration. hinting at the practical role they may play in humanity's expansion into the cosmos. Comets are icy wanderers of the solar system, often called dirty snowballs, because they are composed of a mixture of ice, dust, and rocky material. They originate primarily from two distant regions, the Kuiper Belt just beyond Neptune, and the Oort cloud, a vast spherical shell surrounding the solar system at distances up to 2 light years. These regions act as reservoirs of ancient material, preserving clues about the early formation of the solar system. A comet's most striking feature is its coma and tail, which appear as the icy body approaches the sun. As sunlight warms the comet, ices sublimate, releasing gas and dust into space. Solar wind and radiation pressure then push this material away from the sun, forming two distinct tails, a blue ion tail made of gas and a white or yellow dust tail. These spectacular displays can stretch millions of kilometers, making comets. Visible even from Earth, comets vary greatly in size, from small nuclei just a few hundred meters across to giant bodies several kilometers wide. Despite their small size, they are of enormous scientific importance. They are considered time capsules containing pristine material from the early solar system, including organic compounds and water ice, which may have contributed to the origin of life on Earth. Some of the most famous comets, such as Halley's Comet and Hale-Bopp, have orbits that bring them into the inner solar system periodically, allowing astronomers to observe them repeatedly over decades or centuries. Others have long, unpredictable orbits, spending most of their lives in the distant reaches of space before being nudged toward the sun by gravitational interactions. Humanity has also sent spacecraft to study comets close. As Rosetta mission, for example, orbited Comet 67P, Churyumov-Gerasimenko, and deployed the Philae lander, providing unprecedented insights into the comet's composition, surface structure, and activity. These missions revealed complex features like cliffs, pits, and jets of gas and dust, illustrating that comets are active, evolving worlds rather than static, frozen objects. Comets are more than celestial spectacles. They are keys to understanding the formation and evolution of the solar system. By studying their composition, behavior, and orbits, scientists gain clues about the building blocks of planets, the delivery of water to Earth, and even the potential for life beyond our planet. Each comet that passes through the inner solar system offers a fleeting but valuable glimpse into the deep history of our cosmic neighborhood. In conclusion, our solar system is a remarkable and diverse cosmic neighborhood, a dynamic and intricate system shaped over billions of years. From the small, rocky inner planets like Mercury, Venus, Earth, and Mars, to the colossal gas and ice giants Jupiter, Saturn, Uranus, and Neptune. Each world possesses its own unique features, mysteries, and beauty. Earth, with its life-supporting atmosphere and moon, stands out as a rare cradle of life, while the other planets provide invaluable insights into the forces and processes that shaped our system. Beyond the planets, countless smaller bodies, asteroids, comets, and dwarf planets like Pluto preserve the history of the early solar system. They're time capsules that allow us to study the building blocks of planets and the conditions that made life possible on Earth. Their diverse compositions and orbits remind us that the solar system is not static, but a constantly evolving collection of worlds and objects. Exploration of these celestial neighbors, from robotic spacecraft to orbiters and landers, has transformed our understanding of the cosmos. Each mission, whether to the fiery surface of Venus, the icy plains of Pluto, or the storms of Jupiter, reveals not only the complexity of individual planets, but also the interconnectedness of the entire system. Studying the solar system is more than an academic pursuit. It is a journey to understand our origins, our place in the universe, and the possibilities of life beyond Earth. Every discovery, every observation deepens our appreciation for the vastness, diversity, and wonder of the cosmos. Our solar system is a dynamic, living laboratory, a source of knowledge, inspiration, and endless curiosity. And as we continue to explore, we are reminded that while Earth is our home, it is just one of countless worlds in a universe full of mysteries waiting to be uncovered.